So you've got an electrode. You stick a couple nanometers of hafnium dioxide, high K dielectric, high K, low K, whatever, dielectric on top of that. A thin layer of polyethylene glycol polymer on top of that, say 5 to 10 nanometers thick. On top of that, you stick a DNA origami tile. So this is a piece of DNA that has been routed back and forth on itself into a consistent mechanical structure. DNA is negatively charged. You apply a positive voltage to your electrode and you pull the DNA down into the origami and down into the polymer, and the polymer compresses. And as the polymer compresses, the force that is resisting the DNA being pulled down goes up. And as you sweep the voltage up and down, you basically make this thing move up and down. And you can control how high it moves, how high it goes, based on the amount of voltage you've got. It's a linear actuator, right? This is a nanoscale linear actuator. If this were the Industrial Revolution, this would be your steam piston, your first bit of the steam engine. But it's controlled by voltage. It's on a circuit. You stick a transistor nearby and a piece of charged DNA hanging out one way or another. And as this thing moves, you can actually get the field it's emitting from its charged DNA is gating the transistor. You get more current through your transistor based on where this thing is. So you've got an actuator and you've got an ability to measure where the actuator is, which gives you the possibility of constructing a feedback loop. Then you start using the same DNA origami you made to make the tile to make mechanical structures. So this is the cool thing that has happened in the last 30 years. The biophysicists have figured out how to wrap DNA into interesting, intricate structures that actually have mechanical function. They follow all the laws of mechanical engineering. So we use that. We say, wait, we've made a steam piston, voltage controlled with a feedback loop. We hook to levers to that. And now you've got a thing that moves up and down. It's attached to a lever. The lever moves farther, right? You get mechanical amplification. And once you've got levers and feedback loops, and these things are small enough, you can put several of them near each other and build something called a delta robot. Delta robot is a particularly interesting arrangement of levers and hinges and whatnot, where if you've got a linear actuator and a feedback loop, you can make an end effector move around anywhere you want with 3 degrees of freedom. This is one of the mechanisms people use in robotics and in 3D printing, certain types of 3D printing, to assemble stuff. We posit we can build the same thing out of soft, floppy DNA and make huge arrays of them on a surface. DNA is soft and floppy. It's not an ideal engineering material, but we can build it today. You can plausibly upgrade these things with protein engineering and eventually incorporating inorganic materials. But there's a route today to just build simple nanomanipulator devices in massive arrays out of technology that already exists.